Some relationships between two quantities or variables are so complicated that we sometimes introduce a third variable or quantity to make things easier. In mathematics, this third quantity is called a parameter. And instead of having one equation, say relating x and y, we have two equations, one relating the parameter with x and one relating the parameter with y. Let's have a look at an example. X equals cos t and y equals sin t. That's our parametric equations. We have x and t, the relationship in one equation, and y and t related in the other equation. Let's have a look at what the graph looks like. And to do that, we substitute some values for t into both the equations, and we work out values for x and y. So let's take some values of t and calculate x and y. And we'll take some values of 0, pi by 2, pi, 3 pi by 2, and 2 pi. And to make it a little bit easier, we'll draw the curves of cos t and sin t. Let's go up a little bit more. Cos t, we just put some labels on. And we have 1 and minus 1. So that's our graph of cos t and sin t. And there's sin t. Okay, so when t is 0, x is cos t, and that's 1. When t is 0, y is sin t, and that's 0. When t is pi by 2, x is the cos of pi by 2, which is 0. When t is pi by 2, y is the sine of pi by 2, which is 1. When t is pi, the cos of pi is minus 1. And for y, the sine of pi is 0. When t is 3 pi by 2, the cos of 3 pi by 2 is 0. And the sine of 3 pi by 2 is minus 1. And at 2 pi, when t is 2 pi, the cos of 2 pi is 1, and the sine of 2 pi is 0. So we now have x and y coordinates that we can plot to show the curve. Have our x and our y. When t was 0, x is 1, y is 0. So 1, 0. 0, 1. Minus 1, 0. 0, minus 1. And back again to 1, 0. Now, with those points, we've not actually plotted enough to be able to see what's happening in between these points. But if we were to take values for t between 0 and pi by 2, and some more between pi by 2 and pi, and so on, what we'd actually find is that these are the parametric equations that describe a circle, centre 0, 0, and with a radius of 1. Now, what we often want to find out is how two variables are changing in relationship to each other. So when x changes, how is y changing? What's the rate of change? So we need to be able to differentiate. Now, what we don't want to do is to actually eliminate the parameter and get back to an equation directly relating x and y, because the whole point of having it as a parameter is that it makes it easier for us and simpler. So what we need to do is to find a way of differentiating when we've got them in the parametric form. And that's what we do. Let's write the two equations again. X equals cos t and y equals sin t. And what we're going to do to differentiate is to differentiate each equation with respect to the parameter t. So dx by dt, the derivative of cos t is minus sin t. For dy by dt, the derivative of sin t is cos t. Now, using the chain rule, which says that dy by dt is equal to dy by dx times by dx by dt. What we have here is dx by dt and dy by dt. And what we wish to find is dy by dx. So if we rearrange that equation, dy by dx is multiplied by dx by dt. So to get dy by dx on its own, we divide by dx by dt. We have dy by dx equals dy by dt, all divided by dx by dt. So if we now substitute, dy by dt is cos t, and dx by dt is minus sin t. So what we have is the derivative dy by dx is minus cot t. Let's look at another example, one that's a little bit more complicated. The parametric equations for this example are x equals t cubed minus t and y equals 4 minus t squared. Again, to find the gradient function of the equation, we're going to differentiate each with respect to the parameter. So dx by dt is 3t squared minus 1, and dy by dt is equal to minus 2t. Again, using the chain rule, dy by dx equals dy by dt divided by dx by dt. That is assuming that dx by dt does not equal 0. Let's substitute in. Dy by dt is minus 2t, and dx by dt is 3t squared minus 1. So again, we've found the gradient function of the curve from the parametric equations, but it's in terms of the parameter t. Let's look at another example. This time our parametric equations are x equals t cubed and y equals t squared minus t. So let's have a look at what this curve looks like before we differentiate and find the gradient function. So we're going to substitute for some values of t again to work out some values of x and y so that we can plot the curve. Let's take values of t from -2 through to 2. So when t is -2, x is -2 cubed, which is -8. When t is -2, y is -2 squared, which is 4. Take away -2. 4 take away -2 gives us 6. When t is -1, x is -1 cubed, which is -1. When t is -1, y is going to be -1 squared, which is 1. Take away -1, which gives us 2. When t is 0, then x is 0 and y is 0. When t is 1, x is 1. And when t is 1, y is 1. Take away 1, giving us 0 again. When t is 2, then x is 8. And when t is 2, y is 2 squared 4. Take away 2, giving us 2. So let's plot the curve. Our x-axis and our y-axis. And we've got to go from -8 to +8. So we'll take fairly large steps. So we plot -8, 6, it's up there, -1, 2, 0, 0, 1, 0, and 8, 2. So there's our curve, and here we're not perhaps certain what happens. It does look as if there is a turning point, but let's investigate a bit further and actually differentiate these parametric equations. So as before, dx by dt, the derivative of t cubed is 3t squared. And if we look at dy by dt, the derivative of t squared is 2t minus 1. Again, using the chain rule, dy by dx is equal to dy by dt divided by dx by dt, and again assuming that dx by dt does not equal 0. So if we substitute for our dy by dt, we get 2t minus 1 divided by our dx by dt, which is 3t squared. From this we can analyse the curve further, and we can see that in fact when dy by dx is 0, then t must be a half. So in this section here we do have a stationary point. Also we can see that when t is 0, dy by dx is infinity. So we have got the y-axis here being a tangent to the curve at the point 0, 0. Sometimes it's necessary to differentiate a second time, and we can do this with our parametric equations. Let's have a look at a fairly straightforward example. X equals t squared and y equals t cubed. And what we're going to do is to differentiate using the chain rule as we've done before, and then we're going to apply the chain rule a second time to find d2y by dx squared. So starting as before, dx by dt is equal to 2t, and dy by dt is equal to 3t squared. Using the chain rule, dy by dx equals dy by dt divided by dx by dt, and assuming, of course, that dx by dt does not equal 0. So let's substitute for dy by dt. It's 3t squared divided by dx by dt, which is 2t. And here t goes into t squared t times, so we've got 3 over 2 times by t. Now, applying the chain rule for a second time, we have d2y by dx squared equals d by dx of dy by dx, because we need to differentiate dy by dx again. And that is the derivative of dy by dx with respect to t divided by dx by dt. Now, just to recap, our dy by dx was equal to 3 over 2t, and our dx by dt was equal to 2t. So now we can do the substitution and find d2y by dx squared is equal to the derivative of dy by dx with respect to t. So that's 3 over 2 divided by dx by dt, which is 2t. And that gives us 3 over 4t. So d2y by dx squared is 3 divided by 4t. Let's do one more example. This time our parametric equation is x equals t cubed plus 3t squared, and y equals t to the power 4 minus 8t squared. So we're going to differentiate x with respect to t, which gives us 3t squared plus 6t, and dy by dt is equal to 4t cubed minus 16t. Using the chain rule, dy by dx equals dy by dt divided by dx by dt, assuming dx by dt does not equal 0. So we get dy by dt is 4t cubed minus 16t divided by dx by dt, which is 3t squared plus 6t. Now let's tidy this up a bit and see if there's things that we can cancel. Here at the top we've got 4t cubed take away 16t. So common to both parts of this is a 4 and a t. So if we take 4 and a t outside a bracket, inside we'll have left t squared, that makes 4t cubed, take away 4. Underneath, common to both these parts, is 3t. So take 3t outside a bracket, and inside we're left with t, so that when it's multiplied out we get 3t squared, plus 2. Again, 3t times 2 gives us our 6t. Now we can go further here, because this one here, t squared minus 4, is actually a difference, the minus, the take away, between two square numbers. It's a difference of two squares. So we can express that as t plus 2 multiplied by t minus 2. And that's going to help us because we can do some more cancelling and make it simpler for us before we differentiate a second time. So here, t goes into t once, t plus 2 goes into t plus 2 once. So we're left with 4t minus 2 over 3. Now, differentiating a second time, d2y by dx squared is the differential of dy by dx with respect to t divided by dx by dt. Now, recapping from before, let's just note down dy by dx was 4/3 of t minus 2, and our dx by dt was 3t squared plus 6t. So differentiating dy by dx with respect to t, we get 4/3, and then we divide by dx by dt, which is 3t squared plus 6t. So that gives us 4 over 3 lots of 3t squared plus 6t. So d2y by dx squared is equal to 4, and here we can take another 3 and a t outside of a bracket to tidy this up, 9t into t plus 2. And that's all there is to it.